So we're going to move into big idea number 3, a new concept daily.
All right, so as we said a few times, they really can handle a new concept daily. Now, of course, that's not absolutely every single student, right? It's going to be dependent on who's in your room. Some students are going to need more reinforcement, and that's totally fine. They're going to be going at a different pace, but most of your students are going to be able to handle a new concept daily. So you want to build a culture in your room that when they are first seeing a concept, that they're not panicking if they don't get it. What you want to have that is that, you know what, you are going to see this again and again and again. You don't need to get it the first time. If you don't get it today, it's okay, right? We're just introducing it. So you really want to build that, like it's no pressure, I'm just showing you this is how it goes. And that's even for kids who might be struggling. Still expose them to the new learning. It's important for them to be exposed to it because we never know what kids can do and they can't do. But if we assume that they can't do it and we don't give them the opportunity to at least experience it, then we're doing them a disservice at that point, because sometimes they surprise you. I'd have students that were really quite struggling and they would get something that I didn't anticipate they would, but they had the opportunity and so they were able to do that. So what we want to try to do is always show the why when we're doing the new concept. And don't feel like you have to always understand the why, because there's lots of resources available, either in the resource bank or just Math Antics is wonderful as a resource for this. It's also, which is linked in the resource bank. But the why. So I'm just you can follow along with me if you want. In your containers, you have a toilet paper roll. One of my favorite things to teach geometry with in the world. So if I was talking about circumference, and I might not even call it circumference, I might just say how far around the circle is, or I might not even say that this is what I'm proving. I might just give the kids the material and let them prove it. Depending on the groups, you're going to have all different kinds of entry points for an activity like this. But does anybody happen to know the formula for finding circumference? Shout it out loud and clear. Right, it's diameter times pi. But do we blindly just accept this, or do we want to know why? I'm a big why person. And often, after I showed the kids why it worked, I never had to tell them, like I'd always like, oh, don't sweat the formulas, I'm going to give you the formulas, right? But I never had to after I showed them why it worked, because they remembered. And I'd say, think of the string. And they'd be like, oh yeah. So I'm going to show you the string. You can do this if you want. You can do it in the afternoon. But I'm going to show you why circumference is pi d. So first of all, what is diameter? Okay, can I go anywhere? Like, can I just go like down here? Through the center. Okay, so I'm going to do 1. And those of you, I know it's really tiny. You'll have to kind of trust me at the back. 1. Okay, everybody at the front can concur. That's 1 diameter. Okay, and then I'm going to go 2. Still with me? Okay, and then I'm going to go 3. Okay, do we know a number? It has to do with geometry. That might have a 3 in it. Oh, pi. Okay. So you can tell I'm such a nerd. I love this stuff. So then I'm going to go like this, and I'm going to put it around, and I'm going to say, oh, it goes all the way, but there's a little point. What might that be? Whoa, 0.14, and on and on and on, right? So look at this, you guys. It's 3 diameters. I just showed you 3 diameters and a little bit. So pi becomes in your room 3 diameter, 3 and a bit, right? 3 and a bit, however many digits you care to go to. But we proved it, 3 and a bit. So again, all kinds of different entry points. I might give them the string cut to exactly 3 diameters. I might say nothing. I'm going to say, what circumference? Prove it. I might give them the formula. I might not. So you have all kinds of different entry points. But the kids will look at you like you're a magician when you do that. It's pretty fun. Another example of a way to make the why, or how to make things accessible to kids at all levels, is to do a more complex concept on very simple numbers. So anybody who's ever taught the distributive property knows it's a little complex. Like, it's kind of hard to wrap your head around. It can be. So again, I could start this by saying we're going to talk about distributive property. I could just leave distributive property out of the picture until I've proven what I'm getting them to do. Or I can get them to prove it. So again, there's all different ways you can go about it. So I would show them, like if we took this question, 3 times 1 plus 2, you know, we would be able to do that, right? We would use BEDMAS, and we'd go 3 times 3 is 9. Okay, so we could probably do that even without showing our work. So then I'm going to say, okay, guys, I got a new way. I got a new way to show you that you can do this. And they'll be like, why? And then you might have to say, well, sometimes letters show up, and we have variables, right? We call those variables. We don't know what they are. So sometimes that happens, and that messes us up, and we can't do this. So you could, or you could even not say that. You could just say, look, I'm going to show you a really cool, another cool way we can do this. Look, if I go 3 times 1, and then I add 3 times 2, I get 3 plus 6, and I get 9. Look it, I just showed you a whole new way to do that same question. And you let them do it. You do it a whole bunch of times with easy numbers. You let them do it a whole bunch of easy times. Then you could say, hey, you guys just did the distributive property. And you come and you throw in an x. You throw in a variable. We don't know what that one is. How are we going to do it now? And then you go, and the kids already have such a good understanding of the process that they're not freaking out that there's a letter in their numbers. Why is there a letter in here? You know, so you're just letting them do it on small numbers, comfortable, build that skill, and then you can move on. Okay, so here's another example. Think of how you could use, don't click yet, please. Think of how you could use Post-it notes, or what are those little, what are those little square crackers, those little cheese ones that are thank you, nips. How could we use those or Post-it notes to prove Pythagorean theorem? Which is a squared plus b squared is our hypotenuse squared. Okay, so we'll give you the visual. And so this is fun too, because you could just throw some crackers on the table and say, prove it. Or you could give them some Post-it notes. Or I might give some of my students that are struggling this very thing. Or I might start building it out. But again, in my cumulative review that day, I would have purposely loaded them with perfect squares so that they get that. So if we see here, we go 3 by 3. If we count that up, we know how many squares do we have here, guys? We've got 9 squares. And then here we have 4 by 4. So we have how many? 16. So if a squared plus b squared equals c squared, how many squares should I have here? I've got 9 plus 16 is 25. I've proven it. A squared plus b squared equals c squared. So you could, again, all different kinds of entry points. I'd have some kids where I would just literally throw some Post-its at them and say, this is what Pythagorean theorem is. I want you to prove it. And then again, you could have different supports, different scaffolds for that. But it's just so much clearer when they can see why. Because we can all memorize a formula, but if we don't understand why it works, it's not going to be meaningful to them. Okay, so we talked about that too.